Hello everyone, today I will talk about the paper called NavCoT. The topic is Vision and Language Navigation or VLN. This means an agent moves in a 3D indoor space by following a text instruction. Let me define VLN more clearly. We have an instruction like go down the hall, turn left, and stop near the table. The agent is inside the building and must follow it. At each step, the agent is not given a single best direction. Instead, it is given several candidate views. In this slide, you can see options like A, B, and C. Each option is one possible move. The agent must pick one option or choose stop. So the input is the instruction, the candidate observations, and the history of the past steps. The output is one action at the current step. This looks simple, but the difficulty comes from long instructions and many options. Why is VLN hard? I will highlight 2 points. First, the instruction can be long and has many stages. The agent must know what part it is doing now. It must also plan ahead. If it forgets the progress, it may repeat steps or stop too early. Second, at each step there are many candidates. Many LLM-based methods use captions, so the agent reads text instead of raw images. But captions can be noisy. They may miss small details like a door on the right or stairs behind you. Because VLN is a sequence task, one wrong step can lead to more wrong steps, so error can build up and recovery is not easy. Before LLM-based methods, strong VLM models were usually cross-modal models. They learn vision and language together. They take image features and text features and train them to match well. These methods can do very well on common tests like R2R, so they are strong baselines. However, they also have limits. The models and training pipelines can be complex. Also, when we ask, why did you choose this direction? The answer is not always easy to show in clean natural language. This is why LLM-based methods are interesting. They can produce text listening, but to work well, we need to handle the gap between VLM inputs and normal VLM training data. Now the common LLM-based pipeline is like this. First, for each candidate image, we use a caption model. So each view becomes one short sentence. Then we give the LLM the instruction, the list of captioned options, and the past steps. Finally, the LLM picks an option. This is appearing because the LLM can also output listening in text. It can sound human-like, but there are practical issues. Many early approaches rely on very large and expensive models. Also, the listening task can be long, and long task does not always mean better choice. Sometimes the model writes a good story, but it still picks the wrong option. So the goal is that keep the reasoning helpful, short, and directly linked to the final action. The first core issue is the domain gap. LLMs are trained on web text, books, and chat, but VLN input is very different. We have many short captions, many choices, and a short history. The structure is like a quiz at every step. Also, captions often miss fine details. For navigation, small details matter. Left or right, a door or stairs, or a hallway or a room. If the caption misses that, the LLM cannot recover the missing visual cue. So what happens? Key signals can be buried under noise. The model may focus on the wrong words, and it may still produce a confident explanation even when the action is wrong. This motivates a method that reduces noise and makes the decision process more guided. The second issue is direct action prediction. In many setups, we ask the LLM to pick A, B, or C in one shot, but there is no clear intermediate step like, what should I look for next? Humans often do this. We read the instruction, we form a short goal in our head like find the stairs or look the kitchen, and then we check the scene. This is an important missing step in one short prediction. When there are many options and captions are noisy, one-shot choice becomes unstable. The model can jump to a random option or follow a wrong detail. So NavCoT suggests a simple fix. First imagine the next key thing, then match that idea to one option and only then choose the action. Now I will explain the main idea of NavCoT. The key point is decomposed decision making. The model does not jump straight to an action. Instead, it follows a fixed three-step thinking process at every time step. Why does this help? This because in VLN, the options are noisy. Captions can be wrong or incomplete. If we ask the model to pick an action lightweight, it can get confused. NavCoT as one clear target first. It makes the model imagine what it expects to see next, like a page with a table. Then the model checks the options and picks the one that matches this idea. So the direction becomes more stable and also easier to read. Here is the output format. It has three steps. Step 1 is future imagination. The model says a short phrase about what should appear next. This is usually one landmark or one scene like table or stairs. Step 2 is a visual information filter. The model selects which option best matches the imagination. This forces the model to make a clear link between the idea and the choices. Step 3 is action prediction. The model outputs the final action option to execute. In the example here, it imagines table, then chooses option C as the best match, and finally takes action C. So the output is short, structured, and directly tied to the action. A natural question is, do we have a separate word model here? In this paper, the answer is no. There is no extra network called the word model. Instead, one LLM does multiple loops. When it produces the imagination step, it acts like a simple word model like a mental simulation. It predicts what should come next based on the instruction and the history. Then in the filtering and action steps, the same LLM compares options and makes a decision. So the word model idea is inside the output format and the training, not a separate module. Next, how do they build the input to the LLM? They use a vision to text setup. For each candidate view image, they generate a caption. They also convert the direction info into simple text, like turn left or go forward. Then each option becomes something like option later plus direction text plus caption text. For each time step, the final error input includes three parts: the instruction, the list of options, and the history of the past steps. With this input, the model generates the fixed three-step output we just saw. This slide explains the prompt structure. They want the output to follow the same format every time, so they enforce the format in the prompt. They provide one in context example first. This example shows the exact template for the three steps. Then they ask the LLM to answer in the same structure: imagination, filtered option, and action. After training, they keep using the same prompt structure at inference time, and the action they execute is simply the action option written in the last line, the AP field. So the prompt is consistent, the same template in training and in test. Now how they get training data for this output. The VLN dataset already gives a lot. It gives expert trajectories, which means the ground truth action at each time step. It also gives candidate observation and navigation history, but NavCoT needs more than just the action level. It also needs supervision for imagination step because that is new. And it needs a unified test level for the three-step output so the LLM can learn or generate it. The figure here shows examples of cross steps with the ground truth action and the imagination level at each step. To label the imagination step, they start from the instruction test. They use an LLM to select landmark candidates that are mentioned in the instruction. These are objects or places like bedroom, bed, hallway, stairs, and stable. Why do they restrict to mention the landmarks? First, it makes learning easier and reduces ambiguity. Second, it enforces instruction following because the imagination stays tied to what the instructions talk about. At the bottom, you can see examples from different datasets. The instruction is shown and the extracted landmark list is shown right after it. Now we need to elaborate for the imagination step. This slide shows step 2. We already have the expert action at each time step. That expert action points to the next new next view the agent should move to. So we can treat the next view images as what the agent will actually see next. Now we also have a list of landmark words from the instruction like bedroom, hallway, or stairs. The question is, which one should be the imagination level for this step? The paper matches the next view image with each landmark candidate using a similarity score. Then it picks the best match. The best landmark becomes the ground truth imagination level for this time step. So the imagination level is not random, it is tied to what the expert will see next, and also tied to words that appear in the instruction. Once we have the imagination level, we can build the full level for one time step. The FI level is the selected landmark or short scene place from the matching step. For the next two parts, they keep it simple and consistent. The filtered observation level is set to the expert ground truth option, and the action level is set to the same expert option. This design forces a clean chain. First, the model imagines a target, then it selects the option that matches that target, and finally it executes the same option. So during training, the model learns a stable link between the three fields instead of treating them as a separate task. Now I will explain the training. Training has two stages. Stage 1 is decomposed training. They train three sub-tasks. First FI, predict the imagination place. Second VIF, predict the correct option as the matches observation. Third AP, predict the correct action option. The purpose is to stabilize each skill before asking the model to generate the full three-step output. This matches because zero-shot performance can be weak. The model may output the wrong imagination or it may pick the wrong option even if the imagination is fine. So this stage is like a worm. It helps the model learn each part in a simple way so the next stage becomes more reliable. Stage 2 is full COT generation with imagination learning. Here the supervision target is to the full three-step text output at each time step. The model must follow the exact template, so the input is still the same instruction, options, and history, but now the output is the complete structure test, imagination, filtered option, and action. At inference time, they do the same thing. The model generates the three lines, and they execute the action from the final AP line. The plot at the bottom shows a key point training helps a lot. Compared to zero shot, pre-training improves the results, and binding improves even more. Also, NavCoT tends to beat direct action prediction in these settings. Next is the model backbone and tuning style. They use open LLM backbones like Llama Adapter 7 billion and Llama 2 7 billion. To keep training cheap, they use parameter efficient tuning. That means they do not update all models' weight. They update only a small part. This makes in-domain training more practical. It also helps with scaling because you can train with fewer resources than full fine-tuning, so the pay-specified action is used a reasonably sized OpenVLN and adapted it to VLN with structured levels without needing an expensive GPT-style pipeline. Let me close with the key takeaways and limits. First, NavCoT improves over direct action prediction in many settings. The imagination plus filtering steps help stabilize action selection, and the output is short and structured so it is easier to interpret. But there are still hard parts. One bit limited is the caption-based input. Captions can lose facial detail, and VLM needs that detail. Also, the imagination levels are built automatically, so they can be noisy sometimes. Finally, in absolute performance, strong cross-modal VLM systems are still ahead in many cases. So a natural future step is to combine this idea with stronger vision features, not only captions. Thank you for listening.